El siguiente trabajo es Constructive Heuristic Algorithm in Multi-Start Structure Applied in Distribution System Expansion Planning. Y el presentador es Matheus de Almeida, del Centro de Ingeniería e Ciencias Exactas de la Universidad Estadual do Oeste do Paraná, de Foz do Iguazú, Paraná, Brasil. Así que invitamos a Matheus que se haga cargo de este bloque de tiempo. Bienvenido y el tiempo es tuyo.
Good morning, everyone. My name is Matheus de Almeida. My advisor is Carlos da Rocha and co-advisor Ricardo Freitas. And I'm going to present the constructive heuristic algorithm in multi-star structure applied in distribution system expansion planning. So firstly, we have an example of electric power system represented by generation, transmission, and distribution. And our work speaks about the distribution. So a distribution system has the primary objective of delivering electrical power at the consumption point and ready to be used by electrical energy consumers. So in this context, it's necessary to carry out planning, aiming to establish an adequate path to supply electrical power to consumers. So the distribution system expansion planning, DSAP, is a fundamental process to adapt the system to insertion of new electricity consumers and allow the increase in the consumption of existing ones at the lowest possible costs. So the solution methods employed can be divided into mathematical programming here and heuristic models. In mathematical programming, also known as classical programming, it's usually possible to find optimal global solution. However, the processing time is high and may not converge if the problem is complex. So heuristic models have been applied in solving the DSAP since they can find the optimal solution in a processing time less than classical programming. And here we have some examples as VNS, table search, and constructive heuristic algorithm. So in this context, we need to solve the DSP problem where a set of a topology will be determined in the end. So it's an optimization problem considering objective functions and nonlinear constraints. And to represent the DSAP problem, it's necessary to define mathematical model. In this context, we will use the nonlinear hybrid model, NLHM. The iterative process solution was used as a solution technique with the help of a sensitivity indicator. So our general objective is present the application of a CHA in a multi-star structure to solve the DSAP problem. And the contribution is aligned in modifying the treatment of the system's objective function to obtain a set of solutions and evaluate their respective qualities. And these qualities are related to total cost construction, the minimization of electrical losses, and the voltage profile in the buses. So the constructive heuristic algorithm consists in iterative process of finding solution. At each step of the process, a decision is made to determine the best action allowed in each iteration. So for example, here we have the 10-bus test system, has a substation connected to SE bus, which is connected to bus 2 here. The other lines the other dashed lines here is candidate lines for construction. At this point, I need to know if I should build a line to bus 3, to bus 4, or to bus 5, and so on until the last bus is connected. So in this process, the algorithm considers construction costs and electrical losses and being represented by nonlinear hybrid model. So here we have the nonlinear hybrid model, and the objective function is represented by equation 1, assigned to variable x, z, seeks to minimize the sum of the costs of adding new lines, and this part is the load sharing of buses that have demand. Here, equations 2 to equations 16 represent the constraints of mathematical modeling. Equations 2 and 3 represent the Kirchhoff's first law for the active and reactive power flow for existing and candidate lines. Existing is set B and candidate lines is set U. Equations 4 and 5 represent the Kirchhoff's second law for the active and reactive power flow for existing lines, set B only, here. And equation 6, 8, 11, 14, and 15 represent the relationships between the apparent active and reactive powers and are necessary for the mathematical formulation of the model. Equations 7 and 9 are related to imposition of a capacity limit for the existing lines and candidate lines. Equation 10 represent the fulfillment with the minimum and maximum limits for the bus's voltage magnitude, and equation 12 represent the fulfillment with the minimum and maximum for the apparent power injected in the substation. And equation 16 represent the load sharing bus must be less than demand. So the sensitivity indicator in the algorithm indicates which candidate lines is the best to add in each iteration of the solution construction process. VB here represents the voltage magnitude on the existing bus, set B. Variable X represents the percentage of utilization of line, and parameter C represents the cost of line. And the voltage profile, we use this equation, which VE is the magnitude of the voltage at bus E, and V set is the magnitude of the reference voltage of the bus E. And V proof is a variable that represents a numerical value. So this closer to 0 is the numerical value assigned to this variable. The closer to the reference voltage magnitude are the voltage magnitudes in the system buses, and therefore the voltage profile is better. So the closer to 0 is better for the voltage profile. And here we have the flow chart for the CHA, in which we begin and ET is equal to 0. We have the system bus and line data. We have a definition of number of iteration is equal to 50. Go to iteration update. So ET is equal to ET plus 1. So 0 plus 1 is 1. Update a sets of B, U, and R. Here we have the mathematical model solution. And here we have the first question. Sensitivity indicator is different to 0? If yes, we will choose the construction line in this iteration. And we will update the sets of B, U, and R. If the answer is negative, we have the second question. Variable Z is equal to 0? If yes, we have established radial topology, and we will check if the solution already exists. And how we could this? We check this question. Open circuits different from the radials already existing? If in positive answer, we will have the inserting a new radial solution in the solution set. If no, means that the solution already exists. So here, if the variable z is equal to 0, if the answer was no, we have the poorly conditional system, and here we have this exit. So here we need another question. ET is less than number iteration, definition defined here by 50. If yes, we end our CHA. If no, in negative answer, we have the randomization of weights and applying weights to line costs. So here we have the iteration update too. So the multi-star structure is a logic of that allows the CHA to determine a set of feasible radial topologies with different qualities to solve the problem according to the number of the iterations he initially desired. It's based on strategy that use a random weighting device always after a radial topology is determined, and so we use the application of these random weights to establish the next radial topology. The process is repeated successively until the estimated iteration are completed. So here we have some procedures. And first, the costs ordered in an increasing way. The cost divided by 100. Identify the biggest value of the set and use this value as the basis of division. And then we will have the normalized cost of the other costs. So here we have the random numbers, Rn, modified cost MC, and normalized cost NC. So in this case, the random numbers can vary from 0 to 80. The first range works from 0 to 40 for a decrease representation here. While the second range works from 40 and 8, that represents an increased representation here. Therefore, the idea is to increase or decrease the normalized cost here from 0 to 40 of its initial value. So here we have the two possibilities. In the first, decrease if Rn is less than 40, and possibility of an increase if the Rn is bigger than 40. So here we have a case study to demonstrate the logic. So if we see this line 1 as example, we can see the from bus 2 to bus 3 line. So here we have the graphics of the total cost and electrical losses of the topologies found by the CHA, and in topology 4 is the lowest total cost, and topology 3 was found as electrical losses. In the voltage profile characteristic, here is the total cost histogram, and here this solution was found 9 times by CHA. This solution was found 4 times, and the lowest cost of the system was found 1 time. So here we have the topologies, and in the left we have the original system, and topology 1 as the lower cost final topology. Topology 2 as a lower electrical losses final topology here, and the total cost, electrical losses, and voltage profile. Topology 3 as the second lowest total cost and electrical losses final topology. So here we have the comparison of the 3, and And the difference between 1 and 2 is the construction line 16, 25, and 28. The difference between 1 and 3 is only construction of line 20, 25 here. And the difference between 2 and 3 here is the construction line 16 here, and 28. So in this paper, we present a CHA in a multi-star structure as a solution tool for the DSAP problem, and we could determine a set of radial topologies with different qualities, and these qualities was construction costs, electrical losses, and voltage profile, and that will help the planning engineer in decision making with their respective criteria. Thanks, everyone.
Okay, thank you, Matheus. We will wait only 1 minute for possible questions.
Okay. And sorry again by the internet.
Yes. We are in this new way of do presentations, and it's possible. All the possibilities are. One
Yes.
is internet failing connection.
Yeah. Yes.
Una aclaración, si alguien tiene preguntas, está en el chat donde dice Q&A, questions and answers. Ese es el lugar, hacia la derecha, to the right side of your hoping platform. This is the place for questions. Okay, we have no questions. No tenemos preguntas, así que agradecemos, Matheus. Thank you. We thank you.
Thank you. Thank you.
And continue with your work. Well.
All right. Thank you.
Bye.